Welcome to Seeing the Bigger Picture, Context-Aware Regulations. I'm going to start off by telling you the end of the story so that you have a framework in which to understand the rest of the talk. Databases are commonly thought of as repositories of information, but if we allow them to evaluate rules based on the current environment, they can actually enhance the white spaces. As you will see, there is a potential for huge gains for both primaries and secondaries if we create regulations which take into account aggregate interference and the local state for each whitespace device. When a whitespace device contacts a whitespace database, it provides its location in exchange for a list of available whitespace channels. In between the devices and the databases, we have an API which defines the interface between the two. Having an API allows either side to change while being transparent to the other. It is important to get the API right the first time because although the databases can change and new devices will be introduced, the API will be more or less fixed for compatibility reasons. We argue that we must include a way to change the maximum transmit power in the API for two reasons. One, international harmonization. For example, Ofcom in the UK and the ECC are already thinking about this sort of thing. And two, for future compatibility. It's not important that we know exactly what to do with it yet, but it is important to have this feature in there. So, suppose that maximum power is in the databases. What can we do with it? It's certainly not obvious at this point what the optimal power allocation would be. As this map shows, the variation just in the number of available channels is quite high. In cases like this, economists turn to trading in order to find efficient solutions. The Coase theorem states that in the absence of transaction costs, trading will lead to an efficient outcome. We now turn to a thought experiment on just how such bargaining might play out in the white spaces. Let's take a very specific example in which we have a one-dimensional world with two whitespace channels, red and blue. Each channel has a primary transmitter or two, each with a protected region, shown as colored circles, and a no-talk region, shown in black. If a primary is protected, it means that any TV receiver inside the protected region will still receive and be able to decode TV signals from that tower. For now, we'll consider a set of users which is evenly spaced along the one-dimensional world. Each user is represented by a dot or a pair of dots if he has two channels available. Note that we will use the terms user and location interchangeably. Finally, we need to define a currency before we can begin trading. Since the only constraint is the primary's protection, the natural currency is the amount of interference caused to the primary's receivers. Each primary receiver can tolerate a certain amount of interference. Any more and reception will be lost. This interference budget, combined with the attenuation, for example, we use the ITU propagation model, leads to a natural relative pricing on transmit power. In general, the cost of a unit of power is inversely proportional to the distances to the protected regions. For example, in the blue channel, we see the cost per unit power increasing as we go toward the right. In the red channel, the power decreases and then increases again as we travel between the two primary transmitters. Here we see an example of one transaction that might take place between users A and B. Note that the interference for each TV transmitter is shown next to it as a stacked bar graph. In the red channel, A decreases its transmit power and B increases its transmit power. In exchange, B gives A some money which can be used to buy power from other users. Notice that the total amount of interference to the primaries remains the same, but that the proportions have shifted from A to B. In a second transaction, which need not be with B, but we'll assume that it is for simplicity, A pays B in exchange for power in the blue channel. Again, note that the interference has shifted but not increased. Because each user is now using less expensive power, the total transmit power and therefore utility has increased while staying within the interference budget. Let's fast forward a bit to get an idea of the end solution. First of all, we see that this particular user had no choice but to use the blue channel since he was in the protected region on the red channel. Thus, he is unable to shift his power away from the blue channel. Next, we see locations which are in the opposite situation. For them, power is inexpensive in the blue channel and very expensive in the red channel, so they opt to use only the blue channel. The locations in the middle are in a similar situation, but the price differential is low enough that their optimal strategy is to use both channels. Finally, we see that there are a few locations which are close to the protected region on both channels, making them the most difficult to serve. The Coase theorem seems to give the solution to our problem. Let the whitespace devices trade among themselves in order to arrive at an efficient allocation of resources. However, we haven't actually met the conditions of the theorem. In the real world, there are transaction costs, and here they are significant. There are potentially many participants in this trade, all of whom would need to be able to communicate with one another, which imposes an additional and unnecessary constraint on the whitespace devices. So, it's time to look at an alternative to trading. Although we can't do actual trading, at least not as the default, whitespace databases have near global knowledge which would allow them to simulate the trades between whitespace devices. Unlike humans, wireless devices have very simple desires. They want as much data rate as they can get since all of their value comes through data rate. Because of this, we have a hope of giving a solution to this problem. We cannot possibly account for everything in our simulated trading, so we should hope to offer a good default which maximizes the greater good. The real question is, what is the greater good? One natural goal is to maximize the total power used by whitespace devices while providing sufficient protection for primaries. However, the solution to this maximization problem is easy to predict given the relative prices of power. On each channel, the location or locations with the cheapest power will receive inordinate amounts of power, while all other locations receive none. This is clearly not a good solution. Another natural goal is to maximize the average data rate across locations. When we do this, we see the following power and rate allocations. We've shown this for a very simple one-dimensional world with a single primary at the left. We see that as the distance to the protected region increases, so does the power and hence the data rate. This seems great until you notice that there's approximately 50 kilometers where the data rate is 0, and the results are very similar regardless of the specific objective function. Although these objective functions promote data rate equality, they result in a lot of wasted whitespace and very unequal data rates. What is it about the whitespaces that renders this common objective function undesirable? To see why maximizing the average data rate does not work well in the whitespaces, let's compare the whitespaces with homogeneous spectrum. As we've already seen, the aggregate interference constraint is a weighted sum constraint rather than a sum constraint as in homogeneous spectrum. Since the cost depends on location, we can get more bang for the buck by using power far away from the protected region. Note that we don't see a point mass for the power, as with the previous objective function, since the logarithmic nature of the capacity means we see diminishing returns. The other main difference between homogeneous spectrum and whitespace spectrum is that devices operating in the whitespaces will experience additional interference due to primary transmissions. This compounds the problem of power price by making a unit of power worth less the closer it is to the primary transmitter. At this point, it seems as though it may be important to explicitly incorporate fairness into the objective function if fairness is actually our goal. As a result, we will take a look at the most fair objective function, the max-min data rate. This objective function seeks to provide all locations with the same maximal quality of service guarantee. The optimal solution will have the following properties. Locations which are inside of the protected region on all channels are not considered. However, any location which is outside of the protected region on at least one channel will be given the quality of service guarantee, even if it is an expensive location. Finally, each location should seek to use its cheapest channel first and only migrate to expensive channels if it has no other option. This will help maximize the overall system utility and thus the max-min rate. Rather than using a toy model as in our previous examples, we will test this solution using real-world TV tower data and the ITU propagation model. For simplicity, we have restricted ourselves to the line shown, but we expect our results to hold in 2 dimensions as well. Here we see in blue the protected regions of each TV tower along the line, so you can see that there are a lot more towers near the east coast and west coast than in the center. Here we see the variation in this one-dimensional slice of the United States. On the left, in Berkeley, there are very few whitespace channels. As we travel east through the less populated states, we see that there are more channels available. The number of channels decreases again as we near the populous east coast. Now that we've seen the setup, let's take a look at the objective function. The goal is to maximize the minimum data rate across locations by varying the secondary transmit powers. At each location, we consider the total data rate available rather than the rate achievable on each channel. To estimate the data rate, we use the theoretical Shannon capacity formula, which as you can see in the graph here is logarithmic with SNR. The only constraint in our problem is that of primary protection, also called the aggregate interference constraint. These take the form of weighted sums of powers at each location, so we can see that the constraints are linear in nature. The results of the optimization problem are shown in this graph. For now, let's just look at the far left points and I'll explain the x-axis in a minute. The y-axis is the max-min data rate achievable with the chosen power allocation. I'm not going to go into the details of the algorithms, but essentially we created a set of algorithms which solve the optimization problem in slightly different ways. There are two different types of awareness that these algorithms can have: spatial and frequency awareness. Spatial awareness simply means that you're aware of what other secondaries nearby are doing in your channel. In particular, the spatially aware algorithms take aggregate interference into account and therefore protect the primaries, unlike the others which do not guarantee primary protection. An algorithm which is frequency aware makes intelligent decisions with regards to which channels to use based on the relative cost of power. Of the algorithms that are spatially aware, we see that the frequency aware algorithm does much better than the others. This is because it recognizes the interplay between channels rather than treating each as an all-or-nothing game. Now let's take a look at the x-axis. In order to rule out any pathological cases in our toy model, we allowed each algorithm to remove the minimizing point in an iterative way. We see that the context-aware algorithm is still far outperforming the other algorithms. What we've seen is that with the right APIs, the databases can actually turn into agile spectrum-as-a-service architecture that not only creates more value, but also paves the way for real-time spectrum markets when the whitespaces become congested. For now, we can try to give good defaults by creating context-aware regulations which will be evaluated in real time by the databases.